Hello. So this is the last worksheet in the probability unit. In one worksheet, we'll be covering two different paradoxes. One is called St. Petersburg paradox, and the other one is called two envelopes paradox. So these are separate paradoxes, but they both involve computations with expectation. So it's crammed into one. Let's jump right to it. Okay. Okay, so let's start with Petersburg paradox. So let's say there's a gambling game, and it involves flipping coins until flipping a fair coin until you get heads for the first time. So what happens is that if you get heads right away with one flip, then you'll get $2. If it takes two flips, so on the second flip, you get heads for the first time, so tails and then heads, then you'll get $4. If it takes three flips, so tail, tail, heads, then you'll get $8, and so on. So each time one more flip it takes, you'll get twice as much money as you would have in the previous step. So eventually you'll get heads and then you'll get a payout. So the payout is going to be 2 to the nth power dollars. And that's going to be the prize money. So what I want you to do is take a coin and then see what kind of average payout you'd get in playing 10 games. So flip coins consecutively until you get heads, and then write down. So maybe it takes two flips to get heads first time. Maybe you get heads right away, or maybe it takes four flips until you get your first heads, and so on. So I want you to play out the game several times and then see what kind of average you'll get in the end. So please pause the video and do it now. And if you don't have a coin available, you could go to random.org /coin flipper and do the same thing that we did with the other worksheet as well. So please do it and get a sense of what kind of payout you get on average. Okay. So this is a random game. So I don't know what kind of payout you got on average, but let's say, I mean, this is a game that gives you money, right? So if this was to be a casino game, there should be like a price of admission or how much you have to pay so you can play this game. So if the casino is charging $10 per trial, would you play this game? Like, does your average winning justify the cost per game you'd play? What about $100? What do you think should be the fair price for this game? So let's try to see if we can compute like mathematically what the fair price should be. And then the tool we need is expectation. This is something that we learned in the Four-Bears paradox worksheet. So let's jump to that. Okay. So here's a list of possible payouts: $2, $4, $8, $16, and so on. So each payout following is twice as much as the previous one. And the probability of getting each payout is also decreasing with the factor 1/2, right? So you'll get heads right away with 1/2 probability. If you flipped tails on the first flip, that's 1/2 chance. Then the probability of getting heads next is 1/2 times 1/2, so 1/4, and so on. So each probability of getting heads in each subsequent flip also decreases by probability 1/2, because you get 1/2 chance to get yet another tail. So the formula for expectation is looking at each probability of outcome multiplied by the actual the payout for the outcome. So you multiply these probabilities along with payouts, and then you add up all of them. In this case, there are infinitely many different outcomes. So we kind of have to see, as you add it up, what it gets closer and closer to. And in this case, since the payout happens to be the reciprocal of the probabilities, each of these terms that we add is equal to 1. So 2 times 1/2 is 1, and 4 times 1/4 is 1, and so on. So this sum of expectation turns out to be 1 plus 1 plus 1 plus 1 plus, and so on, which could only be infinity. So does this seem right? So try to think, like, does this correspond to the situation that's happening? When you play this game, do you expect that on average, in the long run, you get infinity dollars, right? Because each time you play, you seem to get a finite payout. Is it possible that every time you play, you get a finite payout, but on average, you're getting infinitely many dollars per game? Does not make sense. So you're welcome to pause and think about this, but it turns out that there is no mistake here, mathematically speaking. The way you interpret it might be a little bit tricky, but it turns out that no, expectation is infinite in this case. And whenever there's infinitely many possibilities, our intuition might not tell us what it's really happening, but actually expectation average payout is infinite, which means in long run average, you'll get more and more money on average per play. What really happens is that these big outcomes where you get long stretches of tails and then heads are so rare that it doesn't pay out very much. But when it does, you get so much money that it counterbalances all the previous plays where you didn't get as much money. And longer you play, the average outcome turns out to be more and more. So you could actually have a situation where every time you play, you get finite money, but on average, you're making more money. So in this situation, there really isn't a fair price you can charge to play this game, because no insurance company would agree to pay out such sum of money, because if they're asked to pay out more money than there is in the world, they wouldn't be able to, right? So yeah, it's surprising, but this game can't be given a price that is fair. Okay, I hope you found that interesting. There's a different paradox we could have with expectation, so let's jump right in. Okay, so this is a two envelopes paradox, and this isn't. This is also a game, but it's not a game you can repeat very many times. So let's say you have two envelopes, and what you know about envelopes is that there's money prize in each of these envelopes, and one of the envelopes has a check for twice as much money as it does in the other. Um, so obviously, you want the envelope with a bigger check, but you don't know which one's which. So it's randomly shuffled. You're given one, and you open the envelope, and let's say you get a check for $500, which is awesome. You're happy to have that, but you're wondering like, well, what does the other envelope have, right? So what's the possibility? It could be twice as much as 500, right? Because one of the envelope has twice as much money than the other. So it's possible that the other envelope has $1,000. It's also possible that the other envelope has $250 because maybe this envelope you got is the bigger one. And because you had 1/2 chance to get smaller or bigger envelope, you might ask, well, let's compute the expectation, right? So let's say X is the payout of what you might get. If you're given the opportunity to, instead of sticking with this $500, switch to the other envelope, right? So there's 1/2 chance that you could end up with $1,000, and then maybe 1/2 chance that you end up with $250. If you do the math, so that's $500 plus 125, so 625. So if you switch the envelope, it seems like you'll get more money, right? On average, because what you got was $500 in your envelope. It seems like if you switch it, then on average, you could get $125 more, at least on average. Because if you think about it, like double or nothing would be a fair bet. But if it's double or one half of what you have, it's slightly more than a fair bet. But so in one hand, it seems like, well, switching is a better deal. You might get $1,000, which is bigger, and so you have $500 to gain or $250 to lose. So it seems like you have more to gain than you will lose. But then, if you kind of think about it, like, don't you always want to switch? So let me lay out the calculation that we just did. Separate PDF here. Okay, all right. So I guess we already did this calculation. So if you had $500, the expectation for switching would be $625. We just did this computation. But let's say it wasn't $500. Let's say it was $80. And you can plug in any number you like, $1 million or $1, it doesn't matter. The other amount of money that the other envelope could have is either half of that amount or twice that amount. So 1/2 times A over 2 or 1/2 times 2A. If you simplify the coefficient and collect like terms, you get 5/4 of the original amount you started with. So 1.25 times the original amount, which seems weird because no matter what you see, you always want to switch the other envelope, but you could have ended up with the other envelope to begin with. Like, it seems weird that expectation computation always suggests that, hey, maybe you should be switching to the other side. Can you find a mistake, or is there a mistake to this computation? I encourage you to pause the video to think about it. Another question that I kind of want to add that I didn't add to this, but okay, if you think you should be switching, how much would you pay to switch? So for example, let's say you got an envelope with $500 and you expect to get $625 if you switch on average. Are you willing to pay $50 to switch to the other envelope? Or are you willing to pay $124 to do that? It seems like you're sinking money into nothing, right? What do you think? So I'll spoil the answer. So there is a mistake in this calculation. And then it comes down to the poorly phrased setup of the problem. You are actually not given enough information to work out what the expectation should be. And really, it comes down to the probability space that you're working with. So sample space is a set of all outcomes. And in this situation, let's say we're working with a situation where we got $500. The outcomes that you could have got with the envelopes is not $250, $500, and $1,000. Those are not possible outcomes of the situation. It was either the true sample space was either 250 and 500 or 500 and 1,000. You know that the 500 was one of the outcomes that you could have had with the shuffling envelopes and looking at one of the checks. So you actually don't know which sample space you lie in. And when you compute the expectation, when you do these type of mixing 250 and 1,000, you are mixing the two different sample spaces together, which is not how we compute expectation. So I hope that made sense. So it's possible that there is a situation where, yes, you do want to switch. There is a situation where you don't want to switch. And there's a situation where you might pay some money to switch. But you're actually not given enough information to work out which situation you lie in. So this paradox isn't really a paradox at all. It's paradox because it was a poorly set up problem where you're actually not given enough information to compute what you need. This computation is false. It looks like it's something that you should be able to compute, but it's not. It's a trick, anyway. So so there were the two paradoxes. So one paradox, St. Petersburg paradox, is the one where you could have a situation where the average payout is infinite, even if the actual payout each time you play might be finite. And then the other paradox is where it was a trick question, basically. You are actually not able to compute the envelope expectation of switching. So if you convince yourself that you always want to switch to the other side, then you're doing something wrong there. And if your gut feeling said that to you, then good job. Your gut was saying the right thing, at least in this problem. Anyways, this concludes the probability section with all the worksheets. I'll also put up another video on kind of reviewing what you should know before the probability unit quiz for Friday. All right, I'll see you there.